For today's Journal Club, the paper we're going to be looking at is a paper by Steven H.Strogatz, and it's called From Kuramoto to Crawford, Exploring the Onset of Synchronization in Populations of Coupled Oscillators. Okay, so I'm going to give a brief overview of the paper first before we go into the details of it. So it's a kind of a review style paper. In at least it gives an overview of, well, at the time it was 25 years, at the time of publishing, which was in 2000, was 25 years of research into the synchronization of coupled oscillators. And it goes through like the main players in the field and the main results. And it starts with Kuramoto himself, who was a Japanese physicist. And we have him to thank for the actual canonical model for coupled oscillators. The Kuramoto model, it's probably the most famous model. And the paper deals with a lot of his early work, his insights into it, mostly analytical, although there were some numerical results towards the end, or towards the later years. And then from his analysis, from Kuramoto's work, the main questions are open questions arising from that. And then moving on to Crawford's contributions, which are mainly on the stability of the system and bifurcation analysis. And yeah, so like the paper, there's a kind of conversational style to it, which I don't know if any of you are familiar with Strogatz and his work. He's actually a very good writer. If anyone has done any dynamical systems, you may have come across the dynamical systems book. I have it here beside me. It's always by my my bedside at night. But yeah, he's an excellent writer, and this is kind of portrayed in the paper, which I think is a nice take. And he gives some anecdotes about his own view or his own time in the field as well, because this is his area, and he actually goes through some of his contributions to the field. Okay, so the background, and this is discussed in the paper. So the Kuramoto model, well, what is it? Basically, it's a canonical model for coupled oscillator dynamics, right? So you have oscillators that are coupled, which means basically to know the state of oscillator I, you need to know the state of all the other oscillators. So in a sense, each oscillator depends on every other oscillator. So that's what we mean by coupled. And basically the main motivation for this model was to describe the phenomena of collective synchronization. And so what is collective synchronization? It's when large systems of oscillators spontaneously lock to a common frequency, despite having their own frequencies. So you get this kind of spontaneous synchronization of the oscillators. And that's what we know about collective synchronization. So this isn't just academic, this is actually fairly important, and we see this a lot in the real world. So we see it a lot in biology and physics. So some examples here, you have in pacemaker cells in the heart. So they control the rhythm of your heartbeat. You see collective synchronization in there, as well as neurons firing in the brain. Fireflies, so if you've ever seen populations of fireflies at night, you see them flashing. They'll all flash at their own frequency, but over time then they actually collectively flash together in synchrony. And as well as that, you have collective synchronization in physics as well. And there's some examples there of superconductors, lasers, and Josephson junctions. Okay, so Kuramoto and Crawford were probably the main two players. It really all started with Kuramoto, but he wasn't the first person to work on this. So Arthur Winfrey was probably the main, well, actually Arthur Winfrey wasn't the very first person to work on it, but he did provide the main initial insights. So he formulated the problem of collective synchronization in terms of limit cycle oscillators. So what's the limit cycle? Well, I have a picture of it up there in the top right. So a limit cycle is essentially any closed trajectory in phase space, right? So here you can kind of see the dark line is this closed loop. And what you'll have with limit cycles is at least one trajectory in phase space will tend to this limit cycle or this closed loop as time tends towards infinity, right? So in the long term, all are at least one trajectory. So Winfrey's key insights, so as well as formulating the problem as limit cycle oscillators, were to have weak coupling. So we mentioned coupling already. Each of the oscillators is coupled together. And he said that if you have weak coupling and then have the oscillators that near identical, right? So essentially every oscillator has the same characteristics as each other. And that each oscillator is coupled to the population frequency, right? So you have a population of oscillators all oscillating around, and that population will oscillate around itself in its own frequency. And so his main insight here was that each individual oscillator is actually coupled to the population in terms of physics. So Winfrey came up with this model, which is basically a model of the phase for the evolution of the phase for oscillator I is given by the intrinsic frequency of oscillator I, so this omega I, plus all the contributions of the influence of the other phases or the other oscillators times some sensitivity function. And this sensitivity function kind of measures the response to oscillator I from all the other oscillators. So it's kind of like a control parameter. And in this model, Winfrey basically discovered one thing, and the main thing was basically that you have this phase transition in time, right? So the system goes from being incoherent, so all the oscillators are oscillating around, essentially minding their own business, and then all of a sudden you get a phase transition to where all the oscillators are synchronous, right? They're oscillating around with the same frequency. So that was Winfrey. And then Kuramoto was aware of this work, and he was inspired by this kind of mean field approach that Winfrey took. And he was able to come up with a model for the long-term dynamics, okay? So essentially in the long-term limit, as time tends towards infinity, these oscillators will tend to this limit cycle, right? And you can see it here in the image I have at the bottom. The way to think of it is you have oscillators kind of running around like the unit circle here. So you have oscillators that are going round and round in the unit circle. And that's essentially the way to view this problem. And he was able to come up with a formula, which is given here. So this is the Kuramoto model. Again, it's a similar model to Winfrey's, but you have a sinusoidal coupling. And this coupling then is controlled by the parameter K, right? It's coupling constant. So that kind of tunes the strength of the coupling between the oscillators. And then he also assumed that there was an initial distribution on the individual frequencies for the oscillators. And his assumptions were this distribution, whatever it is, needs to be symmetric and unimodal. So Kuramoto was inspired by this mean field approach. So he wanted to get a grasp on the global properties of the population of oscillators, right? So kind of get an average view of the oscillators. So what he proposed were these order parameters, right? Which is given here, which are essentially just taking the average of each oscillator, average of all the oscillators, and that will give us a kind of a measure of the overall population over time. So the key parameters here are this R value, which measures the coherence. So that measures like it's a measure of synchronization. So here on the left plot, you have a small R value at 0, which means basically the oscillators are uniformly distributed around the circle. And then this R value will, and then you have the psi parameter, which measures the average phase of the oscillators. So Kuramoto, from that model, basically noticed that you can rewrite the governing equation in terms of this mean field approach, or these mean field parameters, which is given here, right? So now, instead of the old Kuramoto model, we have a model in terms of R, the measure of synchronization, and the average phase of the population. So essentially, this model would suggest that the oscillators appear to be uncoupled, but they're actually not. They are still interacting through the mean field parameters R and psi. And essentially what's happening here in this model, it kind of tells the story of the phase transition that Winfrey saw initially. Essentially, that you have the oscillator, or the phase of oscillator I, will be pulled along towards the average essentially frequency, right? The average, or the phase of the population. And you get this positive feedback loop between the coupling and the coherence, because now the coupling is, or essentially the effective coupling, is a function of the coherence, right? So if you have strong coherence, the coupling is going to be stronger, which means you have more of a pull towards the average frequency. So essentially, if you have oscillators going around, they're going to get pulled more and more towards the average frequency, and then you're going to get this clumping that you see in this plot down here. So as well as that, Kuramoto analyzed what would happen if you vary the coupling strength. So varying the coupling parameter K. What happens? Well, essentially you get two states, right? So he was able to show that for very weak coupling, this is essentially the first state, which is an incoherent state. Essentially the oscillators are moving around, minding their own business. They're essentially uniformly distributed around the circle. And the R value, the measure of synchronization, that will tend to decay over time. So as you vary K then, or you increase K, this incoherent state essentially changes, becomes unstable, and synchronization grows, or the measure of synchronization grows. And you notice that actually this phase transition happens around some critical value, which he called Kc. And he was able to establish that this essentially a bifurcation in the system at Kc. So here you have the bifurcation diagram, K along the x-axis, and then a measure of the synchronization over time, or in the long-term limit. So you go from an incoherent state, increasing K at the transition, you have, you move to a partial synchronized state, and then up towards the synchronized state. So yeah, so all of Kuramoto's results here essentially indicate that they're independent of initial condition, right? It really only depends on the coupling constant K, right? So that would suggest that each K, or each value of K, the system has an attractor. There's actually only one attractor exists for each value of K. Okay, so that was kind of Kuramoto's early analysis of the problem, and from that, there's a lot of kind of questions that could be asked, and it was kind of crying out for an overall theory of the problem. And Strogatz goes on here to say what a good theory should say, or should give. Well, the first two things it should give are a formula for the critical value K, and an expression for the long-term behavior of the synchronization parameter as a function of K. As well as that, a good theory should give you stability results for the incoherent state, right? So the state of where the phases are all uniformly distributed, essentially minding their own business. And as well as that, stability of the bifurcating branch, right? So essentially the branch that you see in the bifurcating diagram that's going up to synchronization. And because essentially there exists an attractor, or there appears to exist an attractor from the numerical results, are there any global stability results that can be gleaned from the theory? And then on top of that, can someone prove convergence results in the long term, or essentially in the limit that then goes to infinity, right? So Kuramoto himself was actually managed to provide results for the first 2 points. He did work on the stability himself, but wasn't successful. He did come up with theories himself. He managed to come up with 2 theories, and they're discussed in the paper, but they weren't correct. But they were actually very close to being correct, which is a testament to Kuramoto, because most of the stuff he did was from intuition. Okay, so Kuramoto's analysis in terms of trying to get expressions for the transition value and the long-term value of the long-term behavior of the synchronization. So what he did was, or how he went about finding this, was to look for steady solutions, right? So in the long-term limit, you would expect, or he assumed you would expect that your synchronization would come to a constant, and as well as your average frequency would come to a constant. In doing so, then, because your average frequency will become to a constant, you can kind of shift frames of reference. So he shifted to a rotating frame. So instead of being in the frame of the unit circle, be in the frame rotating with the oscillators. And in doing so, he was able to set the phases, or essentially the average phase, to 0. And that kind of simplified the Kuramoto model a bit, which is given here. And then from this model, you can see that the oscillators are effectively independent. So you only really have to solve for the individual motions of the oscillators themselves. Now, you need to be careful here, and Strogatz said that Kuramoto used this self-consistent condition, right? So in solving for the individual motions of the oscillators, that would give you values for R and psi, but then you need to check back then that these values of psi and R are matched with the assumptions. Essentially, they need to be constant. So in doing all this analysis, he knows that there are 2 types of long-term behavior. Essentially, the first is when the intrinsic frequencies, so the size of the intrinsic frequencies, is much less than the coupling constant. And then when this is the case, the oscillators will essentially approach the fixed point, right? And the fixed point is given by the value here when this is equal to 0, right? At this fixed point, the oscillators are known as locked, right? Because they've all locked into the same frequency and they're all rotating around, not evolving, essentially. So they're in a kind of locked, well, sorry, they are evolving, but their phase is locked, right? They don't change phase over time. The second state then is when the intrinsic frequency is greater than the coupling constant. And this is where the oscillators would essentially start drifting, right? They're drifting relative to one another. So there were the 2 types of behavior that you can get from this model. Now, he did assume that essentially that R and psi had to be constant, but that doesn't really tie in with or align with the fact that you have oscillators drifting, right? How could you have oscillators drifting and then have the average frequency constant? Was he actually, kind of clever idea is he basically forced the drifting oscillators to have a stationary distribution, right? So they could be drifting around the circle at their own frequencies, but their collective distribution is stationary. And this distribution is given here. And the main insight here, or the main thing to note here, is that essentially the distribution is proportional to the inverse of the velocity of the the oscillators, right? So this is just the right-hand side, the speed of the oscillators. So essentially what this is telling us that on the circle, you have regions of, you have like fast regions and slow regions. So for fast regions, the oscillators are spread out, and for slow regions, they're clumped together. So when that happens, essentially your distribution will be stationary. It actually doesn't change over time. Okay, so from that setting then, he invoked the self-consistency condition, which is given here, right? So essentially, the self-consistency condition, all it is saying that the average behavior of the population is equal to the average behavior of the locked population plus the average behavior of the drifting population, right? So the angle brackets here denote average over the population. So essentially, this needs to be followed, and then using the symmetry of the distribution of the intrinsic frequencies, right? So they're essentially unimodal and symmetric. That's what he assumed. He was able to get an expression for R, right? So remember, we're in a rotating frame, so psi here is 0. So essentially, R is equal to the average behavior of these two. And using the symmetry of the intrinsic frequencies, or the distribution of the intrinsic frequencies, he gets this expression for R. Now, this expression gives you two solutions, or two branches of solutions. The first branch is when R is equal to 0. This is essentially the incoherent state, right? So when all the oscillators are uniformly distributed, oscillating around, minding their own business. And the second branch is the one of interest, right? So when they are in the synchronized state. So he used this branch to find an expression for Kc, so the transition value, and the long-term behavior for the synchronization parameter as a function of K. So how we went about it, well, he set K equal to Kc in here, and then took the limit as R goes to 0, and you get the expression here for the transition value. Similarly, then you get a scaling law for the synchronization parameter R as a function of K, and it's given here. Okay, so as I said earlier, Kuramoto himself, so he was able to knock out the first two open problems. You know, he did work on stability, but he wasn't able to figure it out, or at least they weren't correct. His approaches weren't correct. So Strogatz himself actually managed to make a contribution to this, and his main contribution was to come up with a continuum limit for the Kuramoto model. So in order to work out the stability of the system, you first need to get a continuum limit or a continuum model of the Kuramoto model. And he actually discusses this in the paper. It wasn't obvious to them initially when he started working on it that how you would even go about phrasing the problem. But yeah, anyway, they managed to come up with an idea, and the idea was to phrase it in terms of densities, right? So it's kind of analogous to how you would think of traffic flow or modeling traffic flow. You have this kind of continuum, and this is you've seen in kinetic theory and fluid mechanics. So the idea is for each natural frequency omega, you can imagine a continuum of oscillators that are distributed on the circle, right? And this distribution is given by rho. And because this is a continuum, the evolution of this distribution is governed by this continuity equation here. So V here is rho is essentially the distribution, right? So you're tracking the distribution, how it evolves over time. V here is the velocity, so the velocity here is given by the Kuramoto model. So this is the Kuramoto model just in the continuum limit. And then the mean field parameters again are expressed here, but in terms of the continuum limit. So using all three of these, they were able to come up with an equation for the continuum limit or continuum limit version of the Kuramoto equation, which in its closed form is given here. So like this was kind of a first step towards stability, and it essentially is a fairly significant step, because you can gain all the questions that you'd ever ask. Essentially, you start with this equation, right? Existence, stability, bifurcations of solutions. You essentially start here, and all the previous results that Kuramoto had found can be derived from this equation. So Strogatz then goes on to talk about the stability of the incoherent state, right? So he didn't prove this himself. It was actually proven by Sakaguchi, and he considered a perturbation to the incoherent state, right? So the incoherent state essentially is given by a uniform distribution, right? So the oscillators are oscillating around in a uniformly distributed around the circle, and then some perturbation to this distribution. And from the linearization, he found that essentially Kuramoto had previously conjectured that the incoherent state was stable, or sorry, becomes unstable as you go beyond the transition value. But he also conjectured that the incoherent state was stable, right? Because all the kind of numerical work and analytical work he'd done had suggested such. But actually what Sakaguchi found was that it's neutrally stable. Now what's neutrally stable? Well, it's basically not stable and not unstable, right? I can kind of explain that if you need me to in more detail later, but essentially when this occurs is when the eigenvalues are purely imaginary. So essentially this problem, or the system, has purely imaginary eigenvalues for when k is less than the transition value, so the incoherent state. And then he was able to show then as you vary k, so you increase k past the transition, a real eigenvalue, or essentially the eigenvalue, the real part of the eigenvalue is born, and then kind of moves into the right half plane on the discrete, or essentially the real part of the spectrum. Yeah, and that's pretty much it in terms of the stability. Well, actually, sorry, this is where Crawford comes in. So Crawford was able to take the work from there and essentially add a lot of understanding. So the stability stuff here, there's all kind of linear stability, essentially eigenvalues of matrices, linear stability. He was able to extend it to weakly nonlinear at the transition point. So Strogatz in the paper, they were studying this problem, right? Like, so this is actually kind of a weird problem. Like, how can you have, or, well, we know you can have purely imaginary eigenvalues, but because because you have these values, it causes a lot of problems in the analysis he was doing at the time. And he goes on to discuss some stories he had. So his collaborator, Murillo, I think his name was giving a talk at Warwick about these purely imaginary eigenvalues, and how the real part is created as you transition past the critical value. And someone in the crowd, I think, had basically said, like, this is exactly the type of thing that happens in plasma physics. It's known as Landau damping. And then he goes on to talk about how he actually came across Crawford at a conference, and how he met him, or he basically discussed the problem over lunch. Crawford himself was working on plasma physics, and Strogatz actually came across the paper, like a preprint that was like thrown out on a table at the conference. And anyway, Strogatz essentially introduced Crawford to the problem, and Crawford then was able to go on and provide more results. Yeah, and there's three main papers by Crawford, and Strogatz goes on to talk about them, or at least the main details of those. And here's a summary of them. So Crawford was able to extend the linear stability of the incoherent state to weakly nonlinear stability. He was able to give a derivation of the evolution equation for R near the incoherent state. So Kuramoto had tried previously in his attempts to get tackle stability, but he didn't succeed, or at least he succeeded but was incorrect. But his guess, or his try, was actually very close to the value that Crawford got. And then, as well as that, Crawford then was able to give a proof of the bifurcating branch is locally stable near the threshold in the presence of weak noise. And as well as that, some of the work that Crawford did on this actually had implications for other fields such as plasma physics, fluid mechanics, and kinetic theory.